So thank you all for being here today. I'm glad I'm here too. Everything went as planned. Net result is I have slept 2 hours today. Hope it doesn't show. Today's lecture is going to be about memory. And I'm talking about computer memory right now. There's tons of little things I got to remember. I hope I'll remember all of them. So bear with me if I stumble a little bit left and right. Bit of warning. Today's material is a little bit dry again because we're doing definitions, early on stuff. A lot of these you kind of already know in a way, but I think it's important to nail it down in a more formal way so that we build the foundations for what comes after. And also for further moving forward with your careers, if you ever design systems, I think there are going to be some underlying principles that are good to follow moving forward. So what we're going to be talking about is memory, which is the way computers store data. That's what it is, the storage mechanism. If I were to refer back to the first lecture we did, I told you that if you really want to distill down to fundamentals what a computer does, it does two things. It moves data around, binary quantities, and manipulates them, that it transforms, applies some function to them. These are the two things. So memory is the key mechanism for doing the first one. It's one of those moving data around. There are others, but this is the key one. And memory physically takes many different forms. There is DRAM, there is SRAM, there is flash, there is this, there is that. It used to be there were magnetic cores with wires and stuff like this. And new technologies are coming up, spin torque, whatever. Some of that I don't even understand myself. You rely on people that do material science or physics to do this kind of things. And we care about how a programmer views memory. That's remember, the first half of the course is programmer's hat. How the machine is supposed to behave. How do we exploit it? So what we're going to be talking about today is a specification of what memory is. That is what you should know as a programmer to get so that you can use this device. This is the equivalent. Somebody gives you a car and it tells you this is the steering wheel, these are the pedals, this is what they do. You don't necessarily need to understand the mechanics of it underneath. You don't really need to understand how the turning wheel or the pedal actually works. Right? How does it do what it does? You only need to understand what the effect is. And if you don't believe me in that, I mean, I don't know if you were following the news a few years back with Toyotas. There were these cars supposedly that were accelerating on their own, right? They were starting accelerating. You press the pedal for acceleration. In the old days, it used to be a completely mechanical thing, right? There was like a piece of string that will go to some piece of metal that will open the carburetor, whatever you call it. Sorry, I'm not pronouncing it correctly. It's the thing that mixes the gas with carburetor. Exactly what I said. Thank you very much. I've been trying to fix my accent for a lot of years, and it's not going to happen. Sorry. I am trying still, though. Not too much. Anyway, sorry. That thing, it used to be mechanical. Now it's not. It's like there's a computer that just basically reads how much you press in the pedal and then sends a message to a solenoid to do that. That's why there's a Sansimi accelerator on its own. It's not like a stuck thing. That's why I told you, if you're going to be in the desert, get a Hugo, because it does have the thing, and you can understand what it does. It doesn't do it well, but it does what it does. You understand the whole thing. So we're going to be talking about specification. Now, sorry, I'm trying to keep up on things. So for the case of memory, there's going to be three parts to that. The first is sorry, I'm looking at that. I have to read them myself again. I read them 10 minutes ago, and then I'll try to elaborate a little bit. The first is the types of operations, right? What kind of things it supports. In our case, it's going to be reads and writes. How you specify them. So if you want to say read, what do you say to the memory? What is the information you should provide, and what you should, and then finally is what you expect the behavior to be. This is the specification of the memory. So I'm going to write this wonderful word down because it's important. Specification. And it has these three things I told you about, and they're in the notes. I'm not going to waste time writing this on the board. It doesn't matter at this point. You can go and refer to the notes. The nice thing about the specification, it's like a contract between the designer of the device and the user of the device. You don't have to talk to one another once you agree on these things. You say, this is our contract. I will deliver to you a black box that will do these things. You have to talk to this box in this particular way, and you expect this behavior. How I do it underneath is a different story, right? And let me give you an example. let's say, and this is the difference between specification and implementation. So this is a way of implementing that, of building something that does that. And let me give you an example. Let's say I wanted to build an AND gate. Right? What is the specification of an AND gate? You can say an AND gate is something that accepts two signals. Let's call them A and B. It produces another signal. Let's call it C. And the specification in this case is a truth table, for example. It can take many different forms. Right? And you can say, what you're going to do is you're going to have to give me two values. And if this is a combinatorial circuit, I guarantee you that after a while, the output is going to be that. Okay? This is the specification. And we draw this nice piece thing on paper. This has nothing to do how you implement it. Now, quick question. If I were to ask you to implement an AND gate from scratch, right? Just grab stuff you have home. Right? Could you build one? Seriously? You could? How?
Marbles.
Huh? Marbles? Okay, that's a good example. Tell me about it.
So you have one marble that would go down the path, and another marble that would open the path up. And then if you have two marbles, the one would open the path, the other one would drop through.
So you're thinking of a mechanical construction that will do that. Okay, I think that's the point I wanted to make. I have another example. Anybody else wants to try? Clearly, I'm not talking about you're going to get sand, you're going to take it, bake it or whatever, create a wafer, and then create masks and do these kind of things to do a silicon chip. You could. It just takes a lot of expertise, and it's been developed for many people, by many people over decades. I'm thinking about something else. So marble is a very good example. Another one is you can order something from Amazon. They give you a big box, right? My kids love that. You take the box. So this is the box, okay, just 2D representation. You open two holes. One here, one there, and this is going to be an electrical implementation. Good. So you say this is A, B. You go inside, right? So, or I go inside, whatever, right? Or I go inside. Okay, good. Took me years to reach this level of perfection with drawings. I can teach you. Anyway, so you go inside. You connect this to light bulbs or LEDs if you want to be green. Right? And that's not a bad thing, by the way. I'm not saying this sarcastically. So, or incandescent if you want to be like, I hate everybody, you're all going to go down to flames with me. Okay? So, two lights over there. You're looking at that. Of course, you didn't remember what an AND gate is. If it was somebody else, you give them a piece of paper that says that's what you should do. On the output, you give them a switch. So this is the output. It's a switch, and you either connect this to VDD or to ground. And you tell them, do this. This is a perfect AND gate, perfect. Right? It does the specification, implements the specification. It has exactly the same interface. It does what it's supposed to do. And by the way, if you have a lot of friends, a lot of boxes, you can build any computer you like. Actually, if you build a NAND gate, just give them the reverse of this. So 1, 1, 1, 0. This, as you remember from the previous course, I suppose this is a universal thing. You can implement everything you can think of. Right? Just need a lot of people. That's what it is. So if we're doing this back in the old days, you could actually build a computer. The downside of that is very hard to say details about its actual behavior in terms of latency, whatever. And this brings me to another point. When you have a specification, it is to your advantage as a designer to put as little as possible into that. To say, this is the thing that the device is going to do, and you can leave it at that. If you want, you can keep adding things. You can say, this is going to be an AND gate, and by the way, it's going to operate in 1 second. Maybe a person can do that, right? Oh, this is an AND gate, it's going to operate in 1 picosecond. Good luck with that. I mean, that's a hard circuit to build even today, right? It's a hard circuit. So you can do it, but it's hard. And the more things you put into that, the harder it becomes to, you restrict what are the things you can do, right? It makes it harder for the implementation. So it's better to have as loose a specification as possible, but not something that's vague. It has to be concrete what it does, but don't put too much stuff into it. Okay? Everybody okay up to this point? So today we're going to be talking about specification about of memory. I'm going to give you an example of how memory can be specified, and we're going to talk about its behavioral model. That is, as a programmer, what you expect memory to do. We'll put as little as possible into that, and then the rest is implementation, right? You can have memory that's going to be SRAM, very fast. You can have memory that's going to be DRAM, about 50 times more slower in today's technologies. You can have flash, which is about, I don't remember, 500. If one is 50, the other is 500 for slower. It's about 10 times slower than DRAM, or it used to be. That's how I'm getting these numbers. Or you can have something else if you wish. Okay? Everybody okay with this fast stuff so far? Right. Let me erase that. I have to restrict myself from there to there for the video. So that's why I'm not moving too much. All right, let's talk about memory. So what is memory now? From a programmer's perspective, memory is something that you can use in a way, something like as follows. You can say int A or car B, right? And stuff like this. So this is where these things go. How does this thing work? Okay, good. That's the programmer interface. Right? And memory will be invoked anytime you do something like this, A equals B, right? Or A equals B plus C, or C some other variable, right? Define it if you wish. What's important to understand here is that memory is involved in some of the operations that need to perform these actions. Here you have a read followed by a write. This is read from B and write the result in A. This is two operations that memory has to support. Here you have two reads and one write. Memory does not do this. This is not memory. So there's going to be something else that does the manipulation, right? Memory just delivers data and accepts data and remembers it. Okay? That's what memory does. If you want to have a model of what memory is supposed to be, think of it like a big array, a vector. So big box. Lots of boxes. Usually the number of boxes tends to be a power of 2, 2 to the n. For the system we're going to be using, it's 2 to the 32. Our system is 2 to the 32. Okay. So there are 4 giga of those. Remember, 2 to the 30 is giga, 2 to the 4, 2 to the 2 is 4, that's 4 giga. It's very easy to get what this number means roughly. And then for every box, there are 2 things associated with it. There is a name, and then there are contents. And it's part of the specification what the name is and what the contents are. Again, these are conventions. We're going to talk about the most obvious ones, that are the ones that you should probably assume that every system kind of uses. Okay? The name is also referred to as an address. Most sane systems today use that terminology, but remember, somebody designs a system, it's their system, they can call it whatever they want. Right? So don't be surprised if you find a machine from the 50s or the 60s that has something else, which is actually an address. And what is the address? It's a binary thing. Everything inside the computer is a binary thing. Okay? So this is a binary quantity, and it's going to be a 32-bit thingy. Right? So for the first box, the 32-bit is going to be a lot of zeros. I'm using the 32-bit system now as an example. So this is 32 bits. And the last one is going to be, again, 32 bits, all ones. And usually people refer to this with the arithmetic interpretation. Okay? They're not numbers. They're just addresses. They're names. You can use them and interpret them as numbers if you wish, and you can do calculations accordingly, but they're really addresses. That's what they are, right? If you wish to use the mathematical property that one is after the other, and you can view that as a sequence of numbers, it's very useful for programs, and we're going to use that. But they're just numbers. You cannot read this. You cannot write that. That is the name. Let me say this. This is an immutable thing. This is something you're born with. There is a box that's called 00000. There is a box that's called 00001, so on and so forth. Which box is the 000? Which box is the 001? It's fixed at design time. It's always that box. Can you define memory differently? Yes. Most systems don't. Right? So we're going to stick to what most systems do and what our system does. So this is the address. It's an immutable thing. And we're going to see this is the way to refer to a box and to say, I want to read you, I want to write you. Right? That's the first part. Second thing are the contents. The contents is a mutable quantity. It's again a binary quantity, but it's something you can change. That's where the memory part comes. The write operation is going to change the value that's there. Sorry, I shouldn't have used the value. Use the value in quotes. And the read is going to give you that thing back. It's a thing. What is it? It depends on what you use it for. You can treat it as a number, and we're going to be using numerical representations for those, but it's just a thing. It could actually be a character. It could be banana. It could be whatever you want it to be. It depends how your program uses it. So it has no intrinsic meaning whatsoever. It's just that rather than writing down a bunch of 0 bits or whatever, people tend to write this in a numerical representation. So, for example, the value here could have been 00000001. And I hope you have 20/20 vision because even I cannot read that. That's something that's 8 bits. 7 of them are 0, 1 of them is 1. If you wish, you can think of that as the number 1. It's not necessarily the number 1. It could be a flag. Like if that is anything but 0, then it means do something. Right? That's what I'm trying to say here. You will give it meaning through your program. It's how your program manipulates that. This is mutable. You can change that. The function of the memory is that the values stay what they are unless you change them. Hence the term memory. It remembers what's there. That's the idea here. Notice that I wrote 8 bits here and I wrote 32 bits there. These are design time quantities. The system tells you what they are. When you open the manual of the processor, of the system, will say this is the length of an address. This is how many bits are there. This is the length of its individual box. Okay, so far so good. What else did I want to say? Okay, even though inside the system, I want you to remember this. Even though the system, the 32 bits are always there, when we write things in the notes or when you open manuals, you may see things like that. And they may say this is address 0. Okay, just the number 0. And this is address, I know over here they can say in decimal, for example, 16. I want you to remember that, for example, this is a 32-bit system. The reality is that this is all 32 bits. So there's a representative 0, 0, 0, 0, 1, 0. And all of them are there. Similarly, in here, they may write this number is 0x3. But you do remember from the manual, it was going to say that at every box is a byte, which really means that internally here, the number is actually 0, 0, 0, 0, 0, 0, 1, 1. All the bits exist, and the ones that are not there, they're implied what they are. Right? Somebody may say this is -2. And then you're supposed to remember that they're thinking 2's complement. There's going to be a lot of context there. I mean, you have to go back. Again, you read the Hitchhiker's Guide to the Galaxy. You go down to that planet, to that basement, and you find a note. You know that? Anyway, if you don't know that, that's okay. So you have to remember from some earlier page in the manual, there's something that says that all numbers that are negative are going to be 2's complement for the instructions that manipulate them, which really means that this number is going to be this. You just have to do careful reading, and you have to build a stack of knowledge that you build upon. So far, so good? Okay, so you have to contend with things like that. That's life. Any questions about this so far? Isn't this exciting? Should I do this utopia thing where the scientist comes and says, I'm very excited about this. Good for you. No idea what you're talking about yet. Anyway, that's what memory is. Next thing, I told you it's little things, and I remember them left and right. This is what we call byte addressable memory. Ooh, excellent term. This is byte addressable. All right. Okay. What does that mean? It means that every box is a byte, and every box has an address. Okay. This should make you think that there are systems that are not byte addressable. Again, these are historical things. There may be systems out there today in use that are not byte addressable. Most systems that you're going to contend with in practice are byte addressable. That is, every individual box here is a byte, an 8-bit quantity, and each one of them has a different address. Just to make the point clear, I could have a system that is not byte addressable. It has boxes that are 16 bits. So there are bytes there, but you can only access them in pairs. Right? Something like that. Could be something like this. And if you keep going back in time, you're going to find systems where this is not even a byte. This could be 11 bits. Go figure. All right. The collection of all addresses, this thing, is called the address space. Okay? And this is usually a power of 2 quantity. Why? Because addresses tend to be binary quantities, and you have so many combinations. For the system we're using, as I said, is 2 to the 32. Most systems today have gone up to 2 to the 64. This does not mean that they actually implement every location there. So there are some named locations that don't exist inside the system. It's just that the system is capable. If you were willing to build a system that has 2 to the 64 bytes in there, it will still be able to work with it. Most people don't implement that these days. They have something much smaller than that, 2 to the 40, 2 to the 36. I mean, these are typical numbers. Even though the processor and the interface to memory is capable of supporting up to the 64. Again, our system 2 to the 32. Address space, usually power of 2. You can have as many as you want. You build a system to support a maximum. According to your application, you implement only as much as you need or what you can afford. So you could buy a processor that can support the 4 gigabyte space, but the particular implementation may be using only 2 gigabytes. That's why you can buy phones that have 2 gigabytes, some that have 3 gigabytes, some of them that have 4 gigabytes, still all of them having the same processor inside, because it's the same interface to memory, right? It's just they didn't pay the money to put extra memory in there. All right. Okay, now, next thing. So we define how this thing looks like. Now let's see how we can talk to it. What are the operations that it can support? So we're going to define 2 operations. One of them is going to be a read, and the other is going to be a write. These are the only 2 things that you can do. And this is a notation that I am using. Do not assume that this is a standard notation. Again, this is just so we can get ahead, and also to illustrate the point, you can do whatever the heck you want. As long as you define to people and you give them meaning, they can use it. And that's what everybody's going to do out there. So the first operation is a load, and it takes one operand, which is an address. So you can say, for example, load from location 16. And I wrote that in hexadecimal to impress you with my deep knowledge of everything. Okay? So this is the loading from address 16. What is this supposed to do? It's supposed to go there. It's supposed to give an address that is this, the 001000. That's what's going to happen at the physical level. It's going to go to the box that has the name 16, and it's going to return give you the value that's there. I'm going to give you more examples later on, but that's what it does. How it does that does not concern you. What it says is that once you issue this request to me, you just wait, I'm going to give you the value. That's what it means. There is another one now, which is the store, and not to confuse you and define in a different way that I have it in my notes. In the notes, I have it as store, and it takes 2 parameters, data and address. And these are, again, parameters you have to provide as over here. This returns a value, so data. This does not return anything. You're just saying to memory, please, take this quantity here and write it to the box that has this address as its name. That's all it says. So, for example, you can say store to location 256, for example, the value 5. Okay? So this is going to be, of course, 1000000, and a lot of zeros over here, 32 bits. And this is going to be something like this. Okay? That's what happens underneath. Question?
It's the other way around, right?
Huh?
It's the data first, and then it's the address?
You're absolutely right. See? Okay. I am physically here, though. This means mentally I'm partially here.
For the load.
Huh?
For the load.
Yes, sir.
Where does it put the data it returns?
Very good question. Okay, so the way to think about that is think of it as you have a box of things, right? And there's the memory thing. The memory thing, we have some physical interface. In the case of digital circuits, it will be a bunch of wires coming out of it. In some of those wires, what you do with it, it's your business. How you connect it to other things. Does that make sense? It's like you're buying a board, and it tells you this board has these 2 connections. This goes to power, this goes to ground. These wires are the addresses. These wires are the data for me to write. These wires are the data when you read them from me. And now you have, when you actually design the circuit, you have to connect this appropriately to do what you want. Okay.
So you don't have to specify a data parameter for the load of where the data from that address goes?
It's going to be part of the physical specification of the device, the particular device you buy. It says it goes on these wires. You go solder connections there and you send them wherever you want. You want to send them to a screen so you can look at it, send it to a screen. Just have lights going on and off. That's okay. That's what memory does. It's not a computing device. The only thing, it's really a dumb thing, right? It only does this. It's basically filing things. You just say, remember this for me, give it back to me. Remember this for me, give it back to me. What I do with it, it's a different story. I don't know if this helps. For everybody, an analogy would be, this is like a, think like there is a building and there is the office that is the office of memory. And there is a piece of paper, like a form, think bureaucracy, right? And you say, if you want something from me, you have to fill this form. But it's a decent form. There are three things you have to, there's one thing first. The first question would be, do you want to load, do you want to store? There's a checker box, one of the two. Next question would be, if you're doing a load, give me the address, right? What's going to happen is eventually the clerk is going to go to the back room. They're going to come back and say, here's a piece of paper, here's your data. What you do with that piece of paper is your business. Conversely, if you're doing a store, you check the store box. Underneath there are going to be two things you have to specify, the address and the data. The clerk takes it, says, thank you very much, everything is okay, just go away, trust me when I say this, I'm going to file this. And you trust that it's going to do that. That's what memory is. It's just a front, and you know the interface. What you do with it is your business then in your own circuits. Okay. I hope this kind of makes sense to everybody. Yes? You being nice, or you're following? Sometimes I will horn on people that don't mean anything with that. It's just I have to look at somebody. Where was I? In the beginning there was nothing. And then we wanted to do an example of an operation. This is going to blow you off your socks right now. It's going to be a very, very difficult example to follow. So let's say I have, should I copy the one I have from my notes? Yes, so I don't embarrass myself. I come up with something that's completely ridiculous. So let's say I have these operations now. I do a store to location 0 wax, or the data 1 to location, let's say 1E. Okay. Then I do another store. And let's say we do 2 to location 1E again. And then we do a load from location 0xFF. And then we do another load from location 0x1E. And then we do a store. I'm going to stop now. Okay, don't. Okay, good. I hope everybody's happy with this. Let's see what's going to happen now. So I'm just going to draw the boxes of relevance here. You notice that the addresses I'm using are 1E, 1E, FF, 1E, and 1E. There are really 2 boxes, right? So memory has a lot of them. I'm only referring to 2 of them. So there's going to be the box 1E. So 0x1E. Don't hit me, don't throw stuff at me. 32 bits, remember? Even though I'm writing this, there's really 32 bits there. And then there's the other box, which is the FF box. Okay. And in the beginning of time, there was nothing. You power up the system. Let's assume the system doesn't have random values. Somehow it resets everything to 0. Don't assume that. By the way, that's not true. But for our example, let's assume that that's the case. So I'm writing zeros from both of them. Okay. Now, these are the operations. We have to give a notion of time here. And this is important now. It's not going to become very clear in this lecture why this is important, but trust me, when you take other courses and you start thinking about process or not, this is a very important point now, how you interpret what the machine does and what does that mean about how it does it. Put this in parenthesis note, remember me a year from now or 2 when you take 552 if you do. So I'll give you some hint later on what I mean by that. So there are these steps that I'm doing. What is the interpretation here? This says go to location 1E and store 0, 1. So what's going to happen is it's going to go here and it's going to change this value to 1. Okay? Again, 8 bits always there. The old value is gone, it's forgotten. Up in ether, never to be found again. That's the idea. Now, you go here and you write 2. This one is gone again. Okay, now you may think, why would you even do that? That's not the point. It's just you can. That's what the operations say to memory has to do. That's all there is. The 0 is long gone, the 1 is long gone, now there's 2 there. So when I do the load FF now, I'm going to get the 0. So this is going to get a 0 from here. Okay. This is going to get, obviously, a 2. Because that's the value that's there now. And what this is going to do is going to change, go to 2 and make it a 3. And notice I wrote it in decimal, same meaning, it doesn't matter. As long as you interpret correctly, in binary it's very cool. Everybody okay with this? This is what's called the sequential execution model. This, okay, what am I saying now? When you read programs, at least that's implied in every single case, you read it top to bottom with loops or whatever, you, or I at least, that's what the program is supposed to do, you look at each statement you have there, and you interpret it as if it gets executed one after the other in time. That's why they call it sequential. It's a sequence of things. And there is another underlying property there, that there is what we call atomic operation. That is, there is a point in time where the only thing that happens is this, right? And this completes, what I'm going to say is going to sound funny, completely. So you finish the operation 100%, and then you do the next one. So time is divided into chunks. Every chunk belongs to a different operation, and these get assigned to these chunks in the order you told the machine to do. Okay? This is sequential execution. Now, the reason I'm saying, you may remember me in a year from now if you take 552, there are machines, a lot of the tricks that processors use today, machines used to perform better than before, is they look at what is the ultimate meaning of what you told it, and they don't perform the operations the way you said it they should be performed. They may perform in a different way. They may rearrange them. They may do them in parallel, as long as they can guarantee you that at the end they're going to give you the same result. As long as you understand what this implies to the program and what the program expects is going to be the outcome, you're free underneath in the implementation to go crazy. It's going to be like there is a door. Somebody knocks on the door and says, do that. But there is a party going on there, and they're asking, is there anything happening there? You say, no, everything is, no, I'm just reading, nothing is happening. You close the door, you go crazy, they knock on the door and tell me, did you do what I asked you? Yes, I did. Is everything okay? Yeah, no, nothing. That's how machines operate underneath. It's really going like crazy. If you look at even the thing I have in my pocket right now, right? You give it a program. We haven't talked about instructions, but I suppose you've seen instructions before. When you write the program, you say, I'm going to execute an instruction at a time. No, this thing is looking at 256 at the same time. It looks at what would have happened if you were to execute them one after the other. It goes ahead and says, I'm not going to do that. I'm going to do this. I'm going to do that. It even says, I think this if statement is going to go that way. I don't know, but I think that way. And it does this kind of thing and tries these things, and it works at the end. It's fascinating how it works and how simple it is at the very end. But it took decades to develop this. So it's obvious in retrospect. 552. We'll hint a little of this later on. So far, so good? Okay. All of this is the normal person stuff. Everything up to this point makes sense. Now we're going to go to the points where people have options. And once people have options, they will try all of them. So we'll talk about something else now, and it will make less sense. Okay. Now, when I write a program, I can write character B. And as we discussed last time, this is a byte, usually. However, I can write int A, which is a 32-bit quantity. Now, you could design a piece of hardware that will do 4 requests for the 4 individual bytes that are required to assemble a 32-bit quantity. And you can have the hardware give you back that thing, right? Okay. Memory systems often have that piece of hardware underneath them. So a memory system is not just 2 operations. There are still 2 operations, but they have an extra parameter, which is the data type. So much strength. Okay. Let's call this T. T is a good name. Okay. Type. So there's going to be an extra parameter you can specify, and the T can be B, H, or W. This stands for byte. This stands for word, 4 of them. This stands for half word, like 2 of them. Okay. This is 8 bits, 16 bits, 32 bits. And this is going to be per system. Every system is going to define differently, but these are common data types. Okay. Now, let's see what this means in terms of the specification now. This is so much fun. I think that part is not going to be on the video, those two notes there. Now I realize. Okay. Now, parenthetic note. Rather than drawing memory like the part I erased right now, which was a column, for convenience, so you can fit more data in a single piece of paper, we often do use like a 2D structure for that. So you will find in many notes, including mine, that often I will draw memory like this. Not always, but sometimes I will do that. And I will give you an address for every row. So notice it's a row of 4 boxes. I will write, for example, this is the address 100, and this is the address 104. And because we live in the Western world, the assumption here is going to be this is the address 100, this is the address 101, 102, 103, and then 104, 105, 106, 107. What I wrote on the top, and sometimes that's not going to be there, it's called an offset. It's a distance from a location. This is an absolute position. This is a distance from a location. Offset is a common term that people use in computers. Okay? Now, so this is the equivalent. I'm not going to draw this, but it's equivalent of a stack of 8 boxes. It has 8 addresses, 8 bytes there. Let me write it like this. So these are the values there, 1, 1, 2, 2, 3, 3, 4, 4. And let's do 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now let's do a bunch of operations. Let's pretend that these are the corners of my memory. Yes, miss?
What's the +0, +1, +2, +3?
This is a different representation of this. This is location 100. This is location 101, which I can define that as a distance from 100. This is location 102, 103, and the other one is 104. Okay. The unfortunate part of that is like a long piece of paper, like a, let me not give examples of what kind of forms of paper have this form. So you can draw it like that. It just doesn't fit very nice of a piece of paper. It's like wasteful. It's not very easy for eyes. People usually do something like that. By the way, nothing to do with the reality of how things are really built necessarily. They're mostly built like this. Anyway, I digress, as always. Where was I? Ooh. Wonderful. So let's see now what can happen if I do this. Load byte from location 103. I hope all of you would have been able to say that this is going to give me 44. Okay? How about this? What will this give you, right? A probable answer is this. Now, there's a lot of things that are implied now. Okay. What we gave here is a starting location in memory, the beginning address, 104. It's implied that this is going to access a bunch of bytes in numerical order of addresses, right? And these are going to be adjusted one after the other. How many? Depends on the W, 4. So that's why I took 4, 5, 6, 7, 4 boxes. And then you're going to assemble them in the order of, in numerical order of addresses. Again, I put this first, this second, this third, this fourth. This became the most significant byte. And this became the least significant byte. So think of this as you're going to memory, and remember that thing I said you have to fill in a form, and the form was saying, I want you to do a load, not a store. And here's the address. So you have to specify an address. And the answer from the office is going to be a 4-box thing that says this is the 32-bit quantity you want. So it's going to give you these 4 boxes. You have to think that way to understand what's going on. Internally, memory is going to go and get 4 boxes, and then it's going to assign them in some implied order to the 4 output boxes you're requesting. You're saying, give me this 32-bit quantity. This is what the memory is going to do. Okay? This is called the endianness of the system. Endianness. And it's from the word the end of the world, just remember that, NDNS. Okay? Why is there a word for this? This is a choice, right? I said I can take this, I can take that, I can take this, I can take that. Okay? You guys have done discrete math? Anyway, high caliber math. It's a choice. How many different possibilities are there? Many. Let me tell you how you can think about this. I have 4 boxes to fill, right? For the first box, there are 4 choices. I can take this, 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 and that. Sure? 4 choices for the first one. Once I make the first choice, there are 3 choices for the second one, 2 for the one, so it's 4 factorial. Very nice. So, in theory, people could have, you can have a bunch of people out there that wake up one morning and say, for my machine, I'm going to do that choice. Okay? Good news is they didn't do all of them. So they're not 4 factorial choices. They're really just 2. There is the, I'm going to go this way choice. And this is called big endian. I'll tell you how to remember this thing. And there's the other choice, which is, I'm going to go this way. And you got to know that when you program a machine, because the numbers will look funny if you try to look at what's inside the memory. They will look weird. This is called big endian. This is what I drew over here. The way to remember is you always start from the smallest address, the beginning address, and you fill the boxes starting from the big one, salary. This was a salary. That's where you wanted the digits to change. If it's little endian, this is called little, you start from the little one. Okay? So this goes there. So if this is a big endian system. If this was the little endian system, you'll get this number. Notice how we're going to go now. 7, 8, 5, 6, 3, 4, 1, 2. So I already told you that you fill in reverse order. So you start at the end and you go backwards as you fill. So think I'm always filling that way, but I start on the back or whatever. The other thing to notice is, don't get confused with that. The individual digits don't flip. Remember, this is a hexadecimal representation, which is only for us. There are only bits underneath. The bits are what they are. The boxes themselves don't get interpreted this way or that way. They are what they are. And that's how you transfer them back and forth. It's how you assemble bigger quantities using the individual boxes underneath. Okay? Everybody okay with this? I think this term comes from the Gulliver's Travels book. Not that I read that book. I'm just saying what I've read. And there is a story about the end of an egg or whatever. There are 2 fractions on the island, and they're fighting. One is the big end, the other is the end. So whoever came up with the term, I think they read that book. That's why there's that term in computers. Not that it matters. That's what it is. Most Intel systems, AMD systems, are little endian. Other systems that are now unfortunately not as popular were big endian. There are systems that honestly they're bi-endian, which is you program the beginning when you power up the machine. There is a configuration parameter. You say what you want them to be. And I think when you transfer data over the internet, I think it's big endian, the internet itself. When you package this, and it's always sent as small quantities. But when you assemble them, I think they're simply big endian. Don't quote me on that. It's in the notes somewhere. Find that. One last thing we got to talk about, and then I'm sure I'll remember another one, but for the time being, that's the last thing. We have to talk about alignment. We're all aligned. Okay, so I'm going to give you the let me not give you a definition. Let me give you an example, and maybe you can discover the pattern, and then I can give you the definition. Agree with me? That's an okay definition. So let's start with specific examples, and then we'll generalize to the concept. Okay, load word from location 4. This is aligned. Load word from location 1, from location 5, not aligned. From location 6, not aligned. From location 7, not aligned. From location 8, aligned. First set of examples. Load half word from location 4, aligned. From location 5, not aligned. From location 6, aligned. From location 7, not aligned. From location 8, aligned. And now, let me go this way. load byte from location 4. Is it aligned? Yes. From location 5, this is going to be very fun. Yes. From location 6, yes. 7, yes. From location 8, no, of course not. It's yes. I mean, that would make no sense at that point. Okay? What's the pattern? There's a data type. The data type has a size. The size is 4. Look at the address. Look at the address. Is 4 divisible by 4? High caliber math, yes. Is 5 divisible by 4? No. No, yes. No, yes. Same here, the half word. The data type is 2. 4 divisible by 2. 5, no. 6, yes. 5, 7, no, right? Data type is 1. Everything is divisible by 1, right? That's the idea here. An address is aligned. An axis is aligned. And an axis with a data type is aligned if the address is divisible by the data type's size. Okay? The systems we have require you to write programs that do align axes. If you try to do an unaligned axis, the system has a way of protesting. It's not going to do what you want. And you either they don't protest like this. You're not going to see sparks flying and you're going to say there's something wrong. The system has a silent way of doing that. You have to go and look, something went wrong. If you don't look, your program is going to crash eventually. You won't know why. That's an unaligned axis. You can approach that, that's the way it is, so that I give you a little bit of hint why systems tend to use aligned axes. We have 3 minutes. It has to do with the way memories are implemented. I'm going to erase this now. First, I'll tell you, take this for granted, and I'll explain why aligned axes are good, and then I'll tell you why you should, the first thing I told you, you should take for granted why it's actually done that way. So take it for granted that memory are not organized as a big column. They're organized as rectangular arrays as possible to some degree. So when people build memories physically, they tend to be organized like that, the way we drew them before. And these, depending on the technology, it can be very long rows. Okay. So you have the address 0 is here, the address 1 is here, the address 2 is here, the address 3 is here. And let's pretend this was a system that has 16 bytes per row, just for illustration purposes. This is going to be address 16 now. This is going to be address 31. This is going to be address 32. Let's make it a row, unless it's exactly the row. And this will have gone, anyway, 47, something like, anyway, it doesn't matter. So far, so good? Okay. Now, let's say I want to do, if I do byte accesses, and by the way, the physical interface to that is you say, I want to access a row, and then you say which column you want to access, or which columns you want to access, and the interface is down here. So the wires are coming out down here. There are wires that are running vertically over this. Horizontally, you select which row you're going to read. Vertically, you get the row out. That's the interface from that. That's the addresses. The data comes like that. It's physically built that way. So far, so good? Now, if I'm only accessing bytes, it's not an issue. However, if I'm accessing, let's say, words, I have to access 4 consecutive boxes. If my addresses are aligned and the things are built like that, I have the following property. The 4 boxes will always fall within the same row. Right? That's the key. So with a single access, I can satisfy your request because the addresses are aligned. At the software level, you made things easy for hardware. Okay? So it's a very simple thing. You just write a note on your paper, on the manual, you say, do that. Otherwise, it's not going to work for me. If you want to support unaligned accesses, somebody may say, load word from address 15. So you have to grab this guy, that guy, that guy, and that guy. So 2 row accesses. You have to assemble them and give them to somebody. So if your access latency, for example, was 50 nanoseconds for a single row, it's going to be 50 plus 50, plus the extra logic to do the packetizing, putting things together. So it's going to be at least 100 nanoseconds, twice as slow, just to support aligned accesses. That's why the machine we have does not. It says, you deal with it as a software. I'm not doing it at the hardware level. Everybody with me? Intel's machines, x86 and AMD's machines, because these things were designed in the 70s, and that was not a problem back in the day for various other, the processor was really slow in those days, so they couldn't care less about having to do multiple accesses. It was very natural to do those days they do support underline accesses, and they have to contend with that. But there are the things you can play after that to make it faster. Now, everybody okay with this? You understand why there are line accesses and versus underline? Just remember your system, the system is not, it will pretend, I mean, if you try to execute things, it won't give you a notification unless you go, there's going to be some bit somewhere that's going to say something bad happened. Unless you go and you look into that, you're not going to know. Just give me 1 minute and I'm going to set up. In operating systems, I don't know what Windows does these days. In the old days, you used to get a segmentation fault, like something, illegal memory access kind of thing in Windows. In Linux, you're going to get segmentation violations, something like that. That's what it is. It's in a way. Last thing I want to tell you is why people build rectangular structures as opposed to long columns. It has to do with, first of all, you don't want to build chips that are very long because mechanically they're not very stable. Second of all is that, unfortunately, delay is in circuits, silicon circuits and wires in general, is related to the quadratically with wire length. So if you have a wire that's twice as long, it's 4 times as slow, roughly speaking, versus a wire that's half the size. Okay? So ideally, you would want to have memory to be something like this. Perfect circle again. I know you're impressed. Okay, but these don't fit very nice with the geometries we can build on chips, so they build the closest shape, which is a rectangle, because you have to have wires that are going like that and wires that come like this. That's why they build them like this, and that's why we solve it. If you want to get something out of this, just remember, sometimes we're not done yet. What's up with this? Go. Almost done, almost done.
I need to set up.
Sure. You can come and set up. Yes, please. I'm just going to say one word. You can come and set up. It's not a problem. Where was I? The one thing to remember from this discussion is that sometimes the solutions are not necessarily let's throw resources into something. It's just let's write something on the manual and have people deal with it at the software level. So thank you for your time. Hopefully